Let's take a look at graphing a function with an oblique asymptote, and then secondly one with a hole in it. So to graph this, again, we're going to go back to our steps. If you haven't seen the video previous to this one, or a couple of videos before this, you'll see some steps, and I'm going to go by those steps. First thing I'm going to do is find my vertical asymptote and my horizontal, if any, and any slant, if that's the case here. Okay, so my vertical asymptote would be, after I've factored it, right, I'm going to factor out a 2 at the top, and I get x squared minus 2. Okay, so there's that. I see if I can cancel anything above and below, and I can't. And so then I take what's remaining at the bottom, and I set it equal to 0, and there's my vertical asymptote. My horizontal asymptote is, I go back to my unfactored form, right, to the red one there, and I see that it's top heavy. Well, if my rational function is top heavy, then I don't have a horizontal asymptote, and in addition to that, I want to look for one more thing. If I see that the degree of the numerator is exactly one more than the degree of the denominator, then I am going to have a slant asymptote. So this is the case for this one. The way I find the slant asymptote, I do have one. The way I find it is I take the numerator and divide by the denominator. So let's take this numerator and let's go ahead and fill in the missing term, right, because we're going to use synthetic division. So I'm going to pull the 2, the 0, and the negative 4 off. I'm going to take the denominator and I'm going to set it equal to 0 and go ahead and get my number for the shelf for my synthetic. Alright, so here we go. Bring the 2 down. 2 times 1 is 2. Add up the column. 2. 1 times 2 is 2. Okay, now this right here is my remainder. I don't even look at it. It doesn't matter what the remainder is. All I do is I bring this right here down into the depressed polynomial. The depressed polynomial. And that is my slant asymptote. Isn't that handy? So there's my slant asymptote, and I have a vertical asymptote. So I have two asymptotes that I'm now going to put on the graph. There's my vertical asymptote. And my slant asymptote has a y-intercept of 2 and has a slope of 2. So it's going to go right through here. There it is right there. Now, when you're graphing with a slant, otherwise known as oblique asymptote, the graph is going to approach those the oblique asymptote just like it does the vertical. It's going to get closer and closer to it as the number x gets greater and smaller. In other words, as it approaches infinity and negative infinity. All right, let's go ahead and take a look at our x and y intercepts. And then we'll go ahead and graph a few points. Or excuse me, we'll pick a few points to discover a little more about it. All right, x-intercept is when the numerator is equal to 0. Why? Because that makes the fraction equal a 0, and that's what x-intercept is. We make the y a 0, so we have 2x squared minus 4 is equal to 0, and I end up with, you can do the math on your own, I get square root of 2 plus or minus, and that is a number. It's an irrational, but it's not imaginary, so I'm going to go ahead and put 1.4-ish and 1.4-ish, something like that. So now my y-intercept is when I put in zeros for the x's, so that gives me negative 4 over negative 1, which is 4. So my y-intercept is 4. Okay? So I immediately know what this left side is going to look like. It's going to have this is going to be a curve, right? It's always going to be a curve, and that's going to approach as this gets larger and larger, as x gets smaller and smaller, then it's going to approach the asymptote, that red asymptote. Okay, so there's that curve. Now, I think this other curve might kind of do the same thing, but I'm going to double check by putting in a few points. I do have the 1.4 on the positive, but let me give myself a few more points. I'd like to know what happens at maybe the 2, and then maybe what happens at the 3. Right? Those would be two good points. That's why I say the asymptotes and all the points in place help you to figure out what x values you'd like to, input into your little table. So let's go ahead and calculate those. I put in a 2, I actually get a 1 1/3. I put it back into the original problem, right? And then I put in a 3, So it looks like I get a 2, 1 1/3, and then we get a 3 and a 7. So let me go 1 and a third. Okay, that looks a little bit suspicious, but I'll check it in a minute. And then I go over 3 and I go 7 up. Over 3, 1, 2, 3, 4, 5, 6, 7. Okay, yeah, that 1 and a third looks suspicious. Just a second, let me check that one. Alright, yeah, it was looking a little bit weird. I put in a 2, I get a 4. So there's over 2 up 1, 2, 3. That makes more sense. Now, oops, that's exactly what I thought it was going to do, but that 1 and a third was definitely throwing me off. So I'm going to connect a smooth curve here. And again, this is going to approach infinity up here. Excuse me, it's going to approach the asymptote as x approaches infinity. And then it's going to approach the vertical asymptote going down. Okie doke. Let's take a look at one more. And this is going to be one with a hole in it. So we'll take a look at what happens with that. First thing, vertical asymptotes. Vertical asymptote, horizontal asymptote. Alright, I see that it's bottom heavy right away. I know that's going to be a y equals 0. Vertical asymptote is I want to factor, make sure I factor everything, and then I want to cancel, right? Any factors above and below. That goes in there once, that goes in there once. So really what I have is I have a function that's really just this. That's what the function really is, the reduced version of it. So that's really what I'm going to be working with for the rest of this. Now, what does this mean? The fact that that thing canceled. This right here means that at x is 1, there's going to be a hole. I'm going to have a hole at x is 1. Now, I want to put 1 back in, so I'm going to go ahead and write this. I'm going to have a hole at, let's name the point, at 1. Now, if I put a 1 back in the original, it'll be undefined. So I want to put it back in the reduced, right, form. So I put a 1 back in there, and I get the y value is actually at a half. So there's not an actual point there, but it is, we can locate where the hole is. Okay? It's called a removable discontinuity. All right, now what is remaining, what's remaining in the denominator after canceling is that. That's what I'm going to set equal to 0 so that I can find my vertical asymptote. So my vertical asymptote shows up at -1. My horizontal asymptote is showing up at 0, y equals 0. And I know that I have a hole at 1, 1/2. So once I get it drawn, I'll go ahead and put that hole in there. So let's give ourselves some x and y intercepts. X-intercept, y-intercept, just about finished. And an x-intercept, I'm showing none. Why is it that we have a no x-intercept? Well, we don't have any x-intercept because the whole function here, if I make that a 0, how can that fraction be 0? Well, it can't be because of that 1. So I have no x-intercepts, none. All right, for the y-intercept, right, for the y-intercept, I make x 0. So for the y-intercept, I get, well, looking at the wrong place here, 1, right, okay, I thought it was a 1, so y is 1, right, so I get 1 over 1, which is 1. So y-intercept, make the x 0, and then solve. So I get, let me go ahead and put these in here, or at least this one on here. We've got that point there, no x-intercepts, right, so it's not going to cross that horizontal asymptote. Lastly, let's go ahead and get a couple of points for ourselves. All right, what would you like to know? Would you like to know what's going on at 1 and 2? Yes. Would you like to know what goes on at -1? No, I don't need to know that because it's an asymptote. I do need to know what's going on at -2. So I'm going to go 1, 2, -2. Okay, now actually I'm realizing I didn't check for symmetry on this. And when we look at the symmetry issue, if I put in a -x in both of those locations, I'm not going to get the complete opposite. Okay, I'm not going to get the complete opposite of the whole function, and I'm not going to get the exact same thing, so it's neither. So anyway, just to touch on that. All right, if I put a 1 into this function, and remember I'm putting it back into the original, excuse me, I'm putting it back into the reduced is what I meant to say, the reduced. So if I put a 1 in for x, I'm going to get a half. Okay, well we know what that is, that's the whole. If we put a 2 in, I get a third. If I put a -2 in, I get -1. So let's get some of those points on here. Here we go. Over 1, I get up a half. Now I'm going to make this small because that's actually where my hole sits. and then over 2 up a third. So I already know what this is doing. This is doing this. It's approaching infinity, excuse me for the wiggle there. There's that. And then this is doing this, approaching that asymptote to infinity. Now let's see what's going on at -2. I have a -1. I have a 2, -1. And let's do this. Let's just go ahead and do one more. -3, what's going to happen at -3? I get negative, what, a half? Right? Remember, I put it back in here. So that's -1/2. So at -3, I get -1/2. There it is. So that confirms that my picture does indeed do this. That approaches infinity, approaches the asymptote, and it approaches the asymptote there. Thanks for watching. Hope this is helpful.